Metal tube with electrical current flowing through it is getting hot. We know the reason for that. That's the Joule effect, right? The inner diameter of the tube is 1 mil, and the length of it is 10 mils. You start to flow water through the tube to cool it, and the water begins to boil. So if the water is boiling and we're assuming this is at 1 atmosphere, right? At 1 atmosphere, we know the T of water is 100. Under these conditions, and only convection takes place. So the condition is that our convective coefficient is 5,000 and only convection takes place. So we can ignore conduction. Assuming that the tube has electrical resistance of 8 ohms, and if you guys recall what that means is, if you remember that the difference in voltage equals the resistance times the current, that's Ohm's law is there. Then you do the analogy with the thermal one, right? And this is given in volts, this is given in amps, and this is given in ohms. So that will be the unit for electrical resistance. Then how much current must be applied to the tube in order to maintain an inner surface temperature of 125 Celsius? You may assume that all the electrical power is being dissipated as heat. So let's write this guy down. The electrical power, so electrical power equals current squared times electrical resistance. Okay, and it's saying that all the electrical power can be assumed to be dissipated as heat. So P equals Q. All right, so the idea is, let's zoom in into this beautiful drawing of mine. We have water at 100, it's boiling, and this water is being responsible to take away the energy that's being created because of the electrical current flowing through the tube, right? And then we know that because there's a difference in temperature, delta T drives heat transfer, and therefore we will find a heat transfer Q that will be from the 125 to the 100, right? If we're only considering convection, then we only need to worry about Newton's law of cooling, which tells us that the heat transfer will be the area times the convective coefficient times the delta T. The area in this case is the area of that inner surface there, right? This one here, through which these guys can exchange energy. So that will be 2 pi r times L. And then multiply by H, multiply by delta T. In this case here, we have everything we need. We can do this as 2 times radius, and radius is going to be the 0.5 mil, so 0.5 times 10 to the minus 3 meters, times pi, times h, which was given as 5,000, 1, 2, 3, or actually let's just put it like so we can eliminate the minus 3 there, and our difference in temperature is 125 minus 100, which will give us 25. Unit-wise, we have meters, we have watts per meters squared in Kelvin. Then we have meters again, and we have Kelvin. Right, so we have meters from the length. Where's the length? Then I put the length. Yeah, good. So see, it's always good to check units. So I'm missing one thing there, which is the length of the pipe, and that is 10 mils, so that's 10 to the minus 2. There you go. So now these two meters, kelvins, we're left with watts. This turns out to be 3.93 watts. Back me up on this, please. You can eliminate this guy with this guy here. So it'll be 25 times 5 times pi divided by 100. Okay, that is the amount of heat transfer that we're going to have due to convection inside that tube just there, inside that tube. Now, it's been said that the electrical power, we can assume the electrical power to be the same as the electrical current, the electrical power equal to the same as the heat transfer. So this will also be 3.93 watts. Okay, and if you think about what's happening here is, the idea is that the current that's going through this tube here, incinerating that energy, we achieve steady state so that all the energy that's being created by this current is flowing away into the water in the form of heat. Okay, so if you want to know what's the current that needs to happen for that to reach that equilibrium state there, what we need to do is use this fellow here and say, okay, the current will be the square root of the power divided by the electrical resistance. Note that both these fellows are in watts, so that's fine. And then that will be square root of 3.93 divided by 8 ohms. And this turns out to be 0.49, which means this is approximately 0.7 amps of current. So we need 0.7 amps of current. We need this current to be 0.7 amps over here so that this whole system reaches a steady state in which all the energy being converted into heat due to the current is being dissipated through convection into our boiling water. Any questions?